Substitution. So this is a notoriously difficult topic, probably one of the harder ones for the semester, if not the hardest. Um, Again, that probably towards the end of the semester we'll see maybe some of that series stuff is going to rival this for level of difficulty. But yeah, this is not easy by any means. So what I'm going to do here, you can notice that stuff on the top there. It's sort of giving you an idea about what you should do for your substitution. I'm going to use this first example as a sort of motivator to how this is going to work. What is the trick here? Why it works, perhaps. Um, Typically, when you see any of those forms at the top there, like a square root of something squared minus something else squared, or a square root of something squared plus something else squared, and the somethings being, notice in this case, this is a constant and that is a variable, right? So that's what we're kind of looking for. It's either constant squared minus variable squared, or variable squared minus constant squared, or put a plus sign between them instead. So if you see any of those forms, that's kind of a hint that you're probably going to use integration by trig sub, but that's still not a guarantee because some of these can be done by regular substitution, which I'll show you. There's a couple of examples in here that are like that, in fact. This one definitely cannot be done by regular substitution, so this is definitely a trig sub. Now, what we have to notice here is that this has the form, this is the a squared, right? A squared here is equal to 4. Here, this is telling us that u squared is equal to x squared. And what that means is that a is equal to 2 and u is equal to x in this case. Okay, so all we're doing in this first step is just identifying what is the u and what is the a. Okay. Now that we know that, I'm going to clear this all out of here because I need the room. Now that we know that, we're going to say, okay, if u is equal to x and a is equal to 2, then that thing on the right, just to the right of all of those for integrals involving blank, this form, let u equal, etc. So we've said that u is equal to x. So I'm going to say x now is equal to a. In this case, it's sine theta, because if you look at the form there, a squared minus u squared, that's the first one, and that's what we have here. X is equal to, well, let's see, we said a was 2, so a is equal to 2, or x is equal to 2 sine theta. Now, this seems like a strange thing to do. Like, why would we do this? But we'll see that it actually works fairly well. Now, we always need to remember what happens to the dx as well. So dx is just derivative of x, or du is the derivative of u if you're using u's instead. 2 cosine theta, d theta. So we know that this numerator here, when we see this dx up here, it's going to change into that, into 2 cosine theta d theta. Okay, now the main point of this integration by trig substitution is what's going to happen to that radical term. And so let's see what happens to it with this substitution and why this works so nicely. So x is 2 sine theta, so what I'm going to do is replace the x with what we said it was in the substitution. So 4 minus 2 sine theta, whole thing squared. And look what this does when we do that. When we simplify this, we get 4 minus 4 sine squared theta under the radical. Notice at that point you can factor that 4 out, and we're left with this. 4 times 1 minus sine squared theta. But what is 1 minus sine squared theta? Well, that is an identity, right? This whole thing about integration by trig sub, it depends on this notion of using these Pythagorean identities. Notice that that 4 is also under the radical. Well, we can go ahead and take its square root, take it out of the radical, and then 1 minus sine squared we said was cosine squared. Well, now that's also under the radical, so we can take its square root and just get that. Okay, so that means that that radical term, if you follow those equal signs all the way back, that radical term is going to just change into 2 cosine x. Okay. Now, with all this in mind, and the dx as well, see what happens to the original integral. Well, let's see. Numerator, we said dx is going to change into 2 cosine theta d theta, right? That's the dx that's right here. Dx here becomes this term right here. Okay? Then, what else do we have? In the denominator, we have an x also, right? There's an x there. There's an x right here. Well, what's x? X is 2 sine theta. Okay, so that means that we're going to put the 2 sine theta right there in place of x. Lastly, that radical term, right? We just said what happens to that. That turns into 2 cosine theta, right? 2 cosine theta. So look what we're left with after this substitution, this series of substitutions that we've done. Well, let's see. There's a 2 and a cosine and a 2 here and a cosine here. Those all cancel out, right? And so all we're left with, in fact, here is just a constant, which you can pull out. The 2 is in the denominator, so it's 1/2. And then what's left? What else is left? Well, there's a sine down there in the denominator, right? And then d theta is all that's left in the numerator. Well, that's sine in the denominator is best written like this, as cosecant in the numerator. And so that is the integral that we have now, the integral of the cosecant function. Okay, everybody clear on how we got to this point? Any questions? So now the question becomes, well, how do you find the integral of the cosecant function? Well, that's why we had to do that last section, right? And this is the kind of integrals that we're going to see after we do the trig substitution. We're going to see an integral that involves some combination of trig functions. In this case, it's just the cosecant function by itself. Now, for that one, that works almost exactly like the secant function integral. And so to find it, you just multiply by, and this is one that you can probably just look up on the table from here on out, because once we do it once, we don't have to do it again. Remember how we did that integral of the secant function? We multiplied it by secant plus tangent. Here we're going to multiply by cosecant plus cotangent. Because secants and cosecants are kind of almost the same, right? Secant is just the reciprocal of cosine, cosecant is just the reciprocal of sine. So these integrals should probably be very similar to each other. And I'm sorry, I'm using x's instead of thetas. Let me fix that. These should be thetas, not x's. Theta there, not x. And all these too, I guess. Let me fix that. Okay, so now this just proceeds pretty much exactly how we did it on the secant function. We're going to get cosecant squared on top, and we're going to get cosecant cotangent. And then in the denominator, so all this, and then we'll have the d theta too. And then in the denominator, just this stuff is left. And then you can kind of see where this is going to go, just like I said, just like the secant integral. You can say that u is equal to cosecant plus cotangent, and then du. Gotta remember what these derivatives are. That's kind of why I'm doing this. Derivative of cosecant is negative cosecant cotangent. Derivative of cotangent is negative cosecant squared. So just be aware that this one is the only difference is that we're going to get these negatives for the derivative instead. Now notice that I can actually multiply both sides by -1, and that's going to change the right side to being positive. And then that means the entire numerator becomes negative du, so we're going to get a new integral -1/2 du over u, and that's the same as natural log cosecant plus cotangent. Antiderivative du over u is just ln u. Replace the u back with what it was, and that's what you get. Okay, so with that in mind, then coming back up to here, this is the integral we were just trying to do, right? That came from all that cancellation. I'm seeing I'm putting x's where they shouldn't be. There should be a theta right there. So now we know what that is, right? We know what the integral of cosecant is. So what I'm going to do, I'm just going to come back up to the top and rewrite this stuff since I don't have enough room to put it all on one screen. Let me just rewrite the whole thing. We said that dx over x square root 4 minus x squared became integral, or 1/2 integral cosecant, which then became negative 1/2 natural log of cosecant plus cotangent. Okay, so we're almost there, but we still have to do something else. And this is, partially why this process is pretty difficult, because there's so many steps involved. Notice that now we have an answer, but the answer is in terms of theta and not x, right? So now we have to change the answer back into x land or x world or whatever you want to call it. X is our variable instead of theta. I'm seeing that I'm messing this up again. I'm sorry about the changing these thetas to x's. They should be all thetas right here. Fix all that so we don't make that mistake. Okay, so now if we come back up here and look at our original substitution, it was x equals 2 sine theta. I'm going to come back and write that again. We had our substitution. X was equal to 2 sine theta. That was where we started with this whole thing. This is going to give us the way to change the thetas back into x's, because if you notice now, we can also say that the sine of theta is equal to x over 2. Sine of theta is x over 2. Then we can actually go ahead and draw theta inside an angle, inside a triangle. If I call that angle theta right there, and if I know that the sine of theta is x over 2, remember how sine is defined in a triangle, opposite over hypotenuse, right? X over 2. And then, by the Pythagorean theorem, the other side there has to be the square root of 4 minus x squared. Notice, again, things to notice here. Come all the way back up here. The original integral, actually I can do it right here, I guess. In the original integral, look what was here in the denominator, for the square root of 4 minus x squared. And look what showed up in that third side of that triangle when we drew it. The same thing. That is not a coincidence. In fact, as far as I can tell, that always happens. Anyway, how do we finish the problem then? Well, we need to change these back into x's, right? How can I do that? Well, now I have this drawing here that has theta in it. So I can use that drawing to replace those thetas back with x's. And so I can say finally that minus 1/2 ln absolute value cosecant theta plus cotangent theta. Let's see, what is that going to be equal to? It's going to be equal to negative 1/2 ln. Now what's the cosecant of theta? Well, looking at the triangle again, cosecant of theta, here's the hypotenuse, here's the opposite. How do we define the cosecant in a triangle? We just find it to be the hypotenuse over the opposite, right? Hypotenuse over opposite. And then cotangent, right? Cotangent theta. Here again, here's the theta. How do I define cotangent in a triangle? I define cotangent to be adjacent over opposite, right? So adjacent being this, adjacent over opposite. So that's what it's going to be. That's what I'm going to write there. Adjacent square root 4 minus x squared over opposite x. And then we can notice both of those terms that are inside those absolute value bars are over the same denominator, right? They're both over x. So I can put them over the same denominator if I want to, and write this like this for my final answer. And there it is. There's the final answer for the integration by trigonometric substitution. Pretty difficult, huh? You can see all the steps that are involved to do this. First time seeing it, it's probably like, wow, what did you just do with all that stuff? And why? How do we even know to start with where we started, right? Well, again, that's where that stuff at the top of the page comes in. Just somebody in the past has already done this for us, so we just have to take advantage of that and just trust that those forms that we see at the top of the page are going to work and eventually allow us to figure out antiderivative here. Yeah, well, if you make any little mistake along here, you're going to have problems. You're going to end up with a bad answer, a wrong answer at the end of all of it. And there's a lot of places to make mistakes, as you can see, all along the way here. Now, what I'm going to point out in this next problem is that, or actually in any of these really, what you can do, or what you might want to do at first is just to ask yourself, can the problem be done by regular substitution? And it's actually fairly often, well, maybe not often, but there's a few significant number of times where you maybe can do direct substitution. And sometimes those direct substitutions can actually be a little bit difficult, but probably not as difficult um, as the trig substitutions. Some of them you have to do trig sub. There's just no way around it. In fact, most of the ones in this section are that way. But there are a few where you could say, oh yeah, I didn't even have to do trig sub. And in fact, this problem is one of them, but I'm going to do it by trig sub anyway, just to show you sort of the process, and then also we can compare maybe what is the benefit of if you see that you can do direct or regular substitution. We'll notice that the amount of work that goes into trig sub versus the regular sub is going to be pretty significant difference. So let's do this by trig sub, and then we'll come back, but I think you can probably already see that it can be done by regular sub. But let's do trig sub first and see how that works, just to practice. So first of all, if you look at the form, which of these forms would be appropriate? The first, second, or third one? Does it look like? The second one, yeah. Because there's a plus sign between them. In fact, only one of them has a plus sign between them, so that's got to be the one. So now again, the first step is to just identify. This is just identification. What is u and what is a? Okay? And whatever u ends up being, that's what we're going to set equal to a tan theta. Now, if you just have an x by itself being squared, u is always going to be just that x. But you might run into somewhere that's not the case. Like if you look at example 4, there's a 25x squared there, right? And so in that case, u would be 5x, not just x. So for us, though, in this problem, u is just x. And so I'm just going to say that x is equal to a tan theta. Well, what's a? A is just the square root of whatever that number is right there. And since that's a 5, that means the a in this case is root 5. Root 5. And that means then we're also going to have root 5 and then a tan theta on there. Because we're using the second one, right? All right, so if that's true, let's continue and say what's dx? Well, that's just going to be the derivative of this. The derivative of tangent is secant squared. And so that means that when we see this dx here, we know it's going to become all of that. When we see this x here, that x, we know it's going to become all of that. Okay. Now the last thing that we would need to discover is what is going to happen to all of that. So that's what we'll work on now. What is that going to become? Let's find out. So we're going to say x squared plus 5 to the 3/2 power equal to, well, let's see, what's x? It's root 5 tan theta, right? But that's being squared, so squared, and then plus 5. All this again to the 3/2 power. So we'll square that, and we're just going to get a 5, right? Square root of 5 squared, right? We're just going to get 5 there. 5 tan squared theta plus 5. Just use regular parentheses there. And then that still to the 3/2 power. But now notice we can take that 5 out of there. Now we're left with tan squared theta plus 1. Hopefully that's looking somewhat familiar. Still raised to the 3/2 power. Tan squared theta plus 1. And remember what I said about these. The whole point of these is so that we could take advantage of those trig identities, the Pythagorean identities in particular. So tan squared plus 1 is one of those, right? That is one of the Pythagorean identities. But we know that it changes into secant squared. And also notice that this 5 is also being raised to that 3/2 power. So we have to, or if we want to separate it, we need to write it as 5 to the 3 halves. And then we're going to have the tan squared plus 1 becomes secant squared theta. And that is also raised to the 3 halves power. And so simplifying that, you can see those 2's are going to cancel. We're just left with secant cubed there. We'll have 5 to the 3 halves power, and then secant cubed. Okay, so there we've started now. We've gotten to the point where we figured out what everything in this integral is going to change into. So let's go ahead and change it to its new integral. Minus 5, what's the x? We said x was root 5 tan theta. Tan theta. Okay, so this x right here is what I'm looking at. It became root 5 tan theta, so that's that. Okay. Then we also have the dx, right? What was the dx? That's another root 5. And then secant squared theta. Denominator, what else do we have going on here? We said that entire denominator became 5 to the 3 halves power secant cubed, right? Secant cubed theta. Okay, everybody see what's happening here? Any questions so far? Now, let's take our constants out to the front. We have a root 5 and another root 5 in the numerator, right? Those multiply together to give us 5. And then we're going to have that other 5 there. There's 2 of those 5, so 5. I'm going to write it as 5 squared. And then in the denominator, we've got 5 to the 3 halves. What else happens? Let's see, secant squared here, secant cubed here. And so that's going to leave us with 1 secant in the denominator. So what do we have left now? We have tangent theta over secant theta. Okay, so that's what we're left with. Kind of see why we had to do that last section, right? Section 7.2, because that tan over secant, that's the exactly the type of integral that we were seeing in the previous section. Okay, so how are we going to do that? Well, again, remember that last guideline basically said, well, if you don't really know what else to do, change everything to sines and cosines. And since everything's just to a first power, that would definitely be appropriate here because we don't have any second powers to use any identities. So changing to sines and cosines is a good thing here. Now, the reason I wanted to write this as 5 squared over 5 to the 3 halves is because now we can take advantage of properties of exponents and write that as 5 to the 1/2 power. 2 minus 3 halves is 1/2, or just square root of 5 if you want. I'll change it to that in a second. Tangent we can write as sine over cosine, or sine over cosine. And then that secant, we can write that as cosine in the numerator, right? So that's just going to become cosine. And then look what happens there. Well, then those cosines cancel. And all we're left with is just the integral of sine, which is pretty nice. Root 5 integral sine. Well, that one we don't even have to do anything fancy because we know what the integral of sine is. It's negative cosine, so we're going to get root 5 cosine theta. That's some constant. But again, our last step is that we can't leave this in terms of theta. We have to change it back into x's. And we had our substitution up here. X was equal to root 5 tan theta, right? So x is equal to root 5 tan theta. That means tan theta is equal to x over root 5. Solving for tan theta. Then you can draw your triangle. Some people can do this without a triangle. I still can't. I mean, sometimes I guess I could, but the triangle is like invaluable here. You pretty much have to draw it. Otherwise, you got to be thinking about what the triangle looks like in your head, and kind of hard to hold all that at the same time. Anyway, tan theta, we know that tangent is defined to be opposite over adjacent. Opposite over adjacent. And then the third side is, according to the Pythagorean theorem, x squared plus the square root of 5 squared is just 5, so the square root of x squared plus 5. Okay, and again, if you notice that in fact is the same radical that we had in the beginning of the problem in the first place, right? So now that we have this triangle drawn, we can say what happens to root 5 cosine theta. What is that? Well, root 5, well, what's the cosine theta? We define the cosine to be the adjacent side over the hypotenuse, right? So root 5 over root 5 over square root x squared plus 5. And that is then equal to just 5. Oops, not forget to put c there. C, and then that's equal to 5 over the square root of x squared plus 25. Now, usually when you get a nice simple answer like that, or simple looking answer, I guess, that is actually probably an indication that the problem could have been done by regular substitution. And so let's try this again, and you can see all the work that we had to do to get this one done. With trig sub, well, as we already said, this could have been done by regular sub. So let's see how much easier that is actually going to be. Do the same problem again, and we'll probably get it done in about 2 or 3 lines. So if we're going to do this by regular substitution, we can just say that u is equal to x squared plus 5. And then du is just the derivative of that, which is 2x dx. And then we can divide by the 2 and get 1/2 du equal to x dx. So we know that when we see this x dx right there, we know what it's going to become. It'll become 1/2 du. So we'll have that minus 5, we'll put that in front. 1/2 I'll just put in front as well. X dx became just simply du. Put the 1/2. Denominator was x squared plus 5, so this just becomes u to the 3/2. And we can rewrite that as u to the minus 3/2. And then we can use the power rule on that. The power rule says that we're going to raise that by 1 to 1/2 and multiply the result by 2, so that's going to leave us with just a negative 5. Actually, not even a negative, it'll be positive 5. U to the negative 1/2. Well, what was u in the first place? U was the square root, or sorry, it was just x squared plus 5. Negative 1/2 power. Well, last step here, you can just say, well, move that to the denominator to make it a positive exponent and change the 1/2 to a radical. And so we just get x squared plus 5 square root. And of course, we have x squared plus 25, I mean. No, 5. I don't know what it is. I made a mistake up here. Sorry about that. That should have been a 5, not a 25. So I think you could probably tell, given the choice, you would probably want to do the easier way, and this is clearly the easier way. That, again, of course, that's not always possible. In fact, like I said, for most of these, in fact, I think all the rest of them, that's not going to work. But you might occasionally luck out and get one where it says, do this by trig sub, and you notice it can be done by regular sub. All right, so let's look at number 3. Now, this one is a definite integral, but that's okay. I mean, to find a definite integral, we just have to find an antiderivative. So finding the antiderivative is the trig sub part of this. Okay, now if you look at the form on this one, you can see that whatever you want to make u be, that's the part that has the variable in it, okay? And then the a is just the constant. So if you see the x is x something x squared minus something, the u is the thing that has the x in it, and the a is the constant, okay? When you're trying to decide what form to use. So here, the form I believe is the third one, and so we would say a is equal to 3 here, and again, u is simply equal to x, and again, this is just to identify what's going to happen. So that's telling us that we need to set x equal to 3 secant theta. Dx is then the derivative of that, 3 secant theta tangent theta d theta. And then let's see what happens to the radical. Now I'm going to actually show you how to do this, changing the bounds of the substitution. You don't have to necessarily do it this way, but I'm just going to show it to you. Like if you want to just stick with uh, using trig sub all the way through the integral, the other option is to just simply find the antiderivative of the thing and then come back and then plug in the bounds, right? So you could do that. Or you could do what I'm about to do here, and that's just change all the bounds at the same time that you're following through with the integral. But before we do that, let's figure out what happens to the x squared minus 9. Okay, so what is that? X was 3 secant theta, so we're going to have 3 secant theta squared minus 9. And that gives us 9 secant squared theta minus 9. And then notice that you can factor that 9 out of there. That leaves you secant squared theta minus 1. Now you can kind of see why these forms are the way they are, because when you have this particular form, you want to end up with an identity that you can actually use, right? A Pythagorean identity. And this is one that we can use, right? Secant squared minus 1 equal to tangent squared. We could take out that root 9. Tangent squared. And that just becomes 3 tan theta. Okay, so now let's see what happens to the integral with all this. We're going to get x squared on the top. That's 3 secant theta. 3 secant theta squared dx 3 secant theta tangent theta d theta. All this divided by what we just said that denominator is going to become 3 tan theta. Okay, now this is the part where we have to decide what those bounds are going to become. What is the 4 and the 6 going to become? Now, if you remember it with a regular substitution, the way you decide what the bounds are is you plug them into the substitution that you made. So they, like in a regular substitution, these here are x values and they become u values, okay, in the substitution. And you can change the x values into u values by plugging those x values into the substitution itself. Well, the same thing happens here. If I want to, I've changed this integral into something in terms of x to be something in terms of theta now. And so that means all these values here, x values, these are x values, these new bounds will have to be theta bounds, okay? And how do I determine what those theta bounds are going to be? I plug them into the substitution, okay? So what is the new lower bound? How do I find it? Lower bound. Again, I have to change them into theta values now. I plug them into the substitution. Well, in order to get a theta, I have x is equal to 3 secant theta. I know that. In fact, actually, let me just do it like this. Let me just say bounds in general here. We had x is equal to 3 secant theta, so that means secant theta is equal to x over 3. So what is theta then? Theta is the inverse secant, or the arcsecant, however you want to call it. I'll call it inverse secant of x over 3. And so in the upper bound, what am I going to get? I'm going to get theta is equal to, or theta upper if you want, is equal to the inverse secant. What was it before? It was 6, right? And then over 3. And so that's arcsecant of 2, or inverse secant of 2. Now, for the people who are remembering their trig, that's the same as the angle whose cosine is equal to 2. I'm sorry, 1/2. What angle has a cosine that's equal to 1/2? Again, if you're thinking about your unit circle, I think it's pi over 3. That means that's my new upper bound, pi over 3. The lower bound goes theta lower, whatever. Lower bound. I have to just plug in the old bound. What was the old bound? It was 4. So I plug it in for x, so 4 over 3. Now the inverse secant of 4/3 is not a number that shows up on the unit circle as far as like what angle has a cosine that's 3/4. Well, that's kind of hard to say because it's not on the unit circle. You could use a calculator, but for now, let's just leave it as the inverse secant of 4/3. So my upper bound became pi over 3. My lower bound, I'm just going to leave it as inverse secant 4/3. Okay, with me so far? See what you can cancel here, right? All that stuff's going to cancel. Now look at the integral that we have left after all of this. Look at what is left here. We've got this 3 squared, right? That's going to be a 9, so we can take that out. Then there's a secant there. It's also squared. And there's another secant right there, right? So what does that mean we're going to have left here? Take that 9 out front. Lower bound still this. Inverse secant 4/3. Upper bound pi over 3. What are we left with? Secant cubed. The dreaded secant cubed integral. So that's, again, why we had to do that last section. In fact, this one unfortunately shows up fairly often, probably more often than a lot of the other ones do. The cube of the secant function. But we've already done all that, right? We don't have to actually do it again to solve this problem. So let's just write down the answer that we got for the cube of the secant function. If you remember what that was, it was 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta. And you can go and look at that work that we just did. In fact, just today we did that, right? So, and then our bounds, inverse secant 4/3, and the upper bound pi over 3. This is definitely a difficult problem. Now, the benefit of doing it this way, where we change the bounds, the benefit is that we now don't have to change these bounds back into x's. We can just leave it in theta land and just plug the bounds in and do this fundamental theorem from here. So in other words, we just do the fundamental theorem now. 1/2 secant of the upper bound, which is pi over 3, secant of pi over 3, tangent pi over 3, plus 1/2 ln secant pi over 3 plus tangent pi over 3. Absolute values bars don't really matter too much here. Minus, I have to do this on another level here, minus, what do we get when we plug in the lower bound, the inverse secant? So let's see, there we're going to get 1/2 secant of the inverse secant of 4/3 tangent of the inverse secant of 4/3. And then all that copied again, the second part, ln of all that stuff. Plus, actually that's going to be minus, isn't it? With the subtraction. Minus 1/2 ln secant inverse secant 4/3 minus, or sorry, plus tangent of the inverse secant of 4/3. So a lot going on there. And there's no plus c because this is a definite integral. All right, now we can actually do better than this because we know that, well, we know what some of these things are. So let's, this is all boxed in from the rest of that stuff. So I'm going to go ahead and distribute the 9. I'm going to get 9 halves. What is the secant of pi over 3? Secant of pi over 3 is, I believe, 2. Again, I'm just going from left to right here. Secant of pi over 3. Now we need the tangent of pi over 3. What's the tangent of pi over 3? And again, if we remember that, that's root 3 plus 1/2 ln. I'm going to ditch the absolute value bars because all this stuff's positive. Secant pi over 3 again, it's 2. Tangent pi over 3 is root 3. And then minus 1/2. Now we're on the second part here. What's this going to be? Secant of inverse secant. Well, those just cancel, don't they? Secant of inverse secant. And I got to distribute that 9 too, so it's just going to be 9 halves also. Secant of inverse secant, those cancel. We're just left with 4/3. Now, what about this term here, the tangent of the inverse secant? How do we do that? Let's think about that for a second here. If theta is equal to the inverse secant of 4/3, that means that we can actually draw theta here. And I know that the secant of theta will have to be 4/3. How do we define the secant function? It's adjacent over hypotenuse, so 4/3 there. That means the other side is going to have to be, what is that going to be? No, I did that wrong. Hypotenuse over adjacent, sorry, 4/3 like that. And so that means 16 minus 9 is 7, so the other side is root 7. And so when I want to know what the tangent of that is, what's the tangent of theta then? Tangent's opposite over adjacent, so that's root 7 over 3. Everybody see what I'm doing there? Secant is this, hypotenuse over adjacent. Tangent is opposite over adjacent. And I was trying to figure out what the tangent is because that's what we need right there. So that means that must be root 7 over 3. And then minus, oops, I'm forgetting the 9 there as well. There should be a 9 right there. We'll distribute that 9 to everything. And here as well. Okay, I'll ditch those again. We're just going to get 4/3 there. And then we just said the tangent of the inverse secant of 4/3 is root 7 over 3. So root 7 over 3. A lot going on here. So that's going to leave us with 9 root 3 plus 9 halves. Natural log of 2 plus root 3. These 3's can cancel with that 9. This 2 and this 4 will cancel, leaving us a 2 there. So minus 2 root 7. And then the rest of it, 9 halves ln 4/3. We can even write this as 4 plus root 7 over 3. So all of this is our numerical solution to this crazy hard problem. Yeah, so remember that you wouldn't be doing the arc secant and arc tangent or any of those arc things of an angle. What you would actually be doing them on the output of the angle. Like if you take the secant of something, or if you take the tangent of something, right? So what the best way to do that, I think, like if I ask you to find the inverse secant, well, let's say inverse sine, let's keep it easy here, of 1/2. If I ask you to find that, how do you do that? What is the inverse sine of 1/2? The best way to do that is to just say a sentence for what that actually means. The sentence that you would write here is, this actually literally means the angle whose sine is 1/2. Well, then you have to think about your unit circle and say, well, let's see, what angle has a sine that's 1/2? And it's not just the angle, it's the angle that has the appropriate domain restriction and stuff like that on it. But it's the angle in quadrant 1, basically, whose sine is 1/2. And so what angle has a sine that's equal to 1/2? Well, when you think about the unit circle, sine is the vertical one, right? So shorter distance there. Pi over 6 has that, right? So pi over 6 is the one. If you're having a hard time with this, oh yeah, even those, right? Like, so for the, let's even go to a harder one here, like the, let's do maybe the cosecant of the arc cotangent, even, the inverse cotangent of, I don't know, let's say 2/3. It doesn't matter, anything, right? The cosecant of the arc cotangent of 2/3. How would I do that? This is actually something that you guys saw in your pre-calculus class. It's probably been a while, but this was covered in pre-calculus, exactly this type of stuff. How do you do the cosecant of the inverse cotangent of 2/3? Again, if you want to write your sentence here, you can say that. You can say, what is the angle whose cosecant is the cotangent. I'm sorry, I'm doing this wrong. The angle whose oh, I got to do this another way here. I want to find, and this is probably the way you write this, find the cosecant of the angle whose cotangent is 2/3. If that makes sense. Does that sentence make sense? Find the cosecant of the angle whose cotangent is 2/3. Okay, well, so the way that you would approach that is say, it's an angle, right? Find the cosecant of the angle whose cotangent is 2/3. So let's call that angle, call it theta. Okay, so if I call that angle theta, I put it in a triangle. Well, what do I know about that angle? I know its cotangent, right? I know its cotangent is 2/3. How do you define the cotangent in a triangle? Well, the tangent is opposite over adjacent, so the cotangent is adjacent over opposite. So that allows you to put a 2 there and a 3 there. And then the Pythagorean theorem says that I need to square that and add them together and take the square root, right? That's 9 plus 4 is 13, so that's 13 there. So what is the cosecant of theta then? The cosecant of theta. And that would be the same as the cosecant of the cotangent, or sorry, the inverse cotangent of 2/3, because we called that angle theta. Okay, so how is the cosecant defined in a triangle? It's defined to be the opposite, sorry, the hypotenuse over the opposite, right? And so this would be root 13 over 3. So yeah, just for identification purposes, you remember SOHCAHTOA, you got to remember that, right? SOHCAHTOA, that tells you the basic ones. And as long as you know those, and also the fact that sine inverse is cosecant, right? So if you know what the sine is, you can figure out the cosecant. Cosine, the reciprocal of that is secant. So if you know what the cosine is, you can find the secant. And finally, the tangent, if you know what that is, then you can find the cotangent. So you got to know SOHCAHTOA and you got to know the reciprocals, right? The reciprocal identities and how they go with the other ones. Okay, so I hope that helps a little bit of a review on the trig stuff. If you do need more help on the trig stuff, there's this, in fact, let me just share it with you right now. There's a great video on it. Find it for you real quick. So this person teaches it pretty much the same exact way that I do. She's really good at doing this. In fact, I'll probably share a few more of her videos for you guys because she's really good. If you need some help reviewing trig stuff, unit circle in particular, check that out. In fact, she also has a video on trig substitution, which I'll share with you guys through an announcement in C&M Learn. All right, so that was a hard one, definitely. Difficult problem there. Just so you can see, the alternative way of doing this problem would have been to ignore the bounds. Right? Like we could come back up here and just ignored these bounds. Right? Like these bounds here, we could have just left this as a indefinite integral. And then we could have gone through the whole process of finding its antiderivative, right? The antiderivative would be a big mess. But once we have it and everything's in terms of x, then you could just say, okay, well, now that I've got the antiderivative, now I could just plug those original bounds, the 4 and the 6, these bounds here, back up into the antiderivative, that antiderivative having x's in it instead of thetas. You see what I mean there? In other words, we basically do what we did in problem 1 and 2, getting it all the way back into x, and then we would just plug in the original bounds. So that's perfectly fine if you want to do it that way, if you don't want to bother with this trying to figure out what the new bounds are. The bounds do get kind of weird, as you can see, with the inverse secant and stuff like that. Let's try this one. So this is a good example because it kind of shows what happens when u is not simply just x. Because up till now, we've just been saying, well, u is equal to x. Now, this one, that's not the case. So here we'll have to notice that, again, u is always just the square root of the thing that has the variable with it. And a is always just the square root of the constant. So if you keep that in mind, then that means that in this case, u is going to be 25, or sorry, the square root of that, 5x. And then a is going to be 3. And again, this is just for identification purposes, because now I know that the thing that I'm saying that u is, 5x, that is what I have to set equal to a. In this case, since it's a squared minus u squared, this is a sign substitution, so I'd say 5x is equal to 3 sine theta. Does everybody kind of see what I'm talking about there when I say identify what u is? Whatever that u is, whatever I've said that it is, that quantity is what I'm going to set equal to a sine theta or a tangent theta or a secant theta. Now let's see what that does. Oh, and of course we still have to figure out what dx is. So in this case, we'll have to solve for x. 3/5 sine theta. You got to figure out what dx is. That's important. So dx is going to be 3/5 cosine theta. Okay, and then what happens to this radical term, the root 9 minus 25? What happens to that? 25x squared. It becomes, well, let's see. Keep in mind that this is the same as 9 minus 5x squared. You see that? 5x squared. And so you can see kind of why maybe I wanted to have the 5x equal to that, right? Because there's the 5x now, you see. So with that in mind, this then becomes the square root of 9 minus, well, what does 5x turn into? It turns into 3 sine theta. And then that is squared. Then with that, you can see what you get after you square that whole thing. You get 9 sine squared theta, and the same thing that's been happening for all of these happening again. Factor out that 9, and then you see take the square root of 9, you get 3. That 1 minus sine squared becomes cosine squared, and so at the end of this, we're left with 3 cosine theta. Okay, so with all of that in mind, what happens to this? What does all of this change into? Well, let's see. X we said was, you see there's the x. X is right there. X by itself, and that's what we have here is x squared. So I have to take that 3/5 sine theta. I have to square the whole thing. Dx, we have another 3/5 there. Cosine theta. theta. Denominator, we just said what happens to that. It just turns into 3 cosine theta. So here, be careful with the constants, especially when you have these fractions within fractions and stuff like that. At least we can see that those are going to cancel. Now, I'm going to just write all these constants separately. We have 3/5 squared. That's 9 over 25, right? Because we got to square the whole thing. Then we have another 3/5 there, right? Another 3/5. And then we have that 3 in the denominator. That's just the same as 1/3. So you see what I've done here? 3/5 squared. That's this. 3/5. That's this. 3 in the denominator. That's this. Okay, so I've just taken care of all of the constants, pulled them out of the integral. Okay. Now that all the constants are removed from the integral, we can see what other stuff we have left inside that integral. Well, it seems the only thing that we have left now is the sine squared, right? That's it. Sine squared. Everybody with me so far? Any questions? And then notice 3 cancels here. And what are we left with after we cancel the constants to simplify? 9 and 25 times 5, 125. And so 9 over 125. Sine squared. Now, how do we do the integral of sine squared? Again, this is why we had to do that previous section. How do you do the integral of sine squared? Well, if you remember, that requires the power reduction identity. So that's this. There's your power reduction identity for sine squared. Now that, oops, I'm sorry, I did that wrong. It should be 2 theta, not squared. Okay. And then at that point, then we can do the antiderivative. 1/2, it's easy, that's just 1/2 theta. Now, what is the antiderivative of cosine 2 theta? Well, if you remember, that's just going to be sine 2 theta, but then we have that substitution. A little quick sub you would have to make here would be u is equal to 2 theta, u equals 2 theta. And then you'd have du is equal to 2d theta, and then you'd have to divide by the 2, and that would get you the 1/2. So you're going to end up with that 1/2 there is what I'm trying to say. And then the antiderivative would just be sine 2 theta over 2, or 1/2 sine 2 theta. So that then combines with the other 1/2 that we have there, and we're going to get 1/4 sine 2 theta. Okay, so let's go ahead and distribute this. That's going to be 9 over 250 theta minus, if I multiply that by 4, 250 times 500, right? So it's 9 over 500, I guess. Sine 2 theta. Okay, now at this point we would go back and say, well, what was our original substitution? Come back up here, and we saw that 5x was equal to 3 sine theta, right? 5x equal to 3 sine theta. So that tells us that sine theta by itself is equal to 5x over 3. And so now I can draw a triangle that has that theta in there. We'll know what the sine of that theta is. That'll be 5x over 3, so sine is opposite over hypotenuse, right? And then by the Pythagorean theorem, you would square the hypotenuse and then subtract from that the square of the other side there, right? So 9 minus 25x squared. And again, if you notice, that quantity that's on that third side of the triangle is in fact the same as the radical term that we had in the original problem, right? Again, I have not found a problem where that doesn't happen, so I've done probably hundreds of these at least. Okay, so now we got to use that drawing to come back over here and change these back into x's. Okay, so in fact, I've got to quick way to figure out what theta by itself is, right? There's a theta sitting there by itself. Theta by itself, without any sign or anything like that, I just got to solve this thing for theta. So for that, I can say theta is equal to, let's see, put it here. Theta is equal to the inverse sine of 5x over 3. So that's what this is going to become right there, that theta right there. Now, for that sine 2 theta, that's a little bit harder to deal with because we don't have a drawing for 2 theta. We have a drawing for theta. So unfortunately, the only thing we can do there is use a double angle identity to change that back into something that just has thetas and not 2 thetas. So here we have to remember our double angle identities. So there's a lot of trig here. So here I'm going to have 250, 9 over 250 theta minus 9 over 500. If you guys remember what your identity, double angle identity for sine is, sine 2 theta is equal to 2 sine theta cosine theta. And just remember that this is a double angle identity here. This double angle identity to this. So you got to remember those two. If you don't remember them, definitely look them up because there's only one for sine. The one that's in fact the most important one. The one for cosine we may use occasionally, but there's actually 3 of them for cosine if you remember that. So look them up if you don't remember what they are. So with that in mind, now we're almost ready to change these back into x's. Let's just simplify this a tiny bit more. This is equal to 9 over 250. Now that 2 that goes along with the other one, we can cancel the 500 in the denominator. That also becomes 9 over 250. And we'll get a sine theta. Oops, I forgot the theta there. Sine theta, cosine theta. Finally, changing all this back. 9 over 250. Theta by itself, we said that was the inverse sine of 5x over 3. Minus 9 over 250. Sine of theta. Now I'm looking again here. So this is the theta. Sine of theta is opposite over hypotenuse, so 5x over 3. X over 3. Cosine theta, now I'm here. Cosine theta is adjacent over hypotenuse. So that becomes square root 9 minus 25x squared over 3. C. Final simplification here, and we'll be done with this crazy problem. The 9 will cancel with both those 3's here. The 5 and the 250 can cancel. And what is that? 50, I guess, will be left there. So our final answer here is 9 over 250 inverse sine 5x over 3 minus, what do we have left there? 1/50th, I guess, is the only constant that's left. 1/50th x and square root 9 minus 25x squared. And so there we go. There's our final answer for that one. So I'm trying to show you like again, as we have usually been doing, trying to show you like every possibility that you'll run into on the homework. Although some of these, of course, they're just going to be not exactly the same as the ones we've seen here. As goes with pretty much every technique of integration. It takes a bit of creativity. You've got to kind of use what you've learned in other problems to figure out maybe how to do something that you have not seen before. But I'm trying to hit every one that I can here, at least as far as what you might expect. So this is one of them, and the important thing here to take away from this one was that u was not simply x here, right, at the very beginning. That was an important thing to notice there. Now let's do another one where it doesn't look really at all like it would even fit any of the forms for trig sub. So that be number 5, example 5. Again, this one doesn't seem to fit any of the forms. It doesn't have a squared plus a u squared in the denominator, or an a squared minus a u squared, or any of the three. And yet, we're still going to do trig sub on it. X squared, 4x plus 8. Again, it doesn't look like it's going to match any of those forms. However, there's a way that we can force it to match one of those forms. And remember, the forms require us to have something squared plus something else squared. And one of those somethings has to have the variable in it. And the other one is just a constant. So something squared that involves an x plus something else squared, that's a constant. Okay? Anybody remember how to do that? How to change this trinomial into something that actually will be a binomial, something squared plus something else squared? There is a way that we can change it. Remember what that is? Well, it is a quadratic, but the technique I'm looking for is how do we change this into another form, where it's something squared plus something else squared. So really, you can factor it, but that's not going to do it. Quadratic formula is just going to like tell us what the zeros of that thing are. But if you remember, there's a way that we can change this. It's called completing the square, and that's what we're going to do here. We're going to complete the square. And how do we complete the square? We look at the middle term, which in this case is 4, the middle coefficient really, 4, that's what we look at. We take half of that number and square it. Okay, so half of 4 and square it is actually 4, right? So that tells us that we're actually going to add 4 to this. Oops. I'm going to add 4 to this without changing it. So I also have to subtract 4. And then I still have that plus 8 on the end. Okay, so really, if you can see what I've done here, I've simply added 0, right? Plus 4 minus 4. But it's really the same as the thing that was on the left. But this is the whole point of completing the square. Because if you remember, by doing that, half of that term and squaring it, this now becomes a perfect square trinomial. What does it factor to be? X plus 2 quantity squared, right? Then the rest of this stuff, you just have to subtract it, right? So it's going to end up giving us a plus 4 on the end of that. So that means that this can now be rewritten as x plus 2 squared plus 4. And lo and behold, it is now written as something squared plus something else squared, right? And that is exactly what we want for using the integration by trig substitution. So that means this integral is the one we now need to find, x over x plus 2 quantity squared plus 4. And then now, since it's written in that way, we can identify our u, and we can identify our a. Well, the thing that's being squared is now x plus 2. So this is another one where the u is not simply just x. And then the a is the square root of the other term, that's just 2. Both of those things together, again, tell us that we now need to set x plus 2 equal to 2, in this case, tangent theta, because it's got a plus sign between them. And again, we need to find du. So maybe we could solve this for x. X is equal to minus 2 plus 2 tan theta. So dx is just the derivative of that. 2 secant squared theta. D theta. Okay, so far. So taking care of the x and the dx, now we got to take care of that term that is in the denominator. Oops, I'm forgetting that actually is under a radical, isn't it? So, okay, what happens to that radical term then? X plus 2 squared plus 4 under the radical becomes what? Well, we said x plus 2 by itself became 2 tan theta. And then that's squared. And there's a plus of a 4 there. And then we get 4 tan squared theta plus 4. And again, this hopefully is starting to look familiar. And then take the 4 out of there, we're left with tan squared theta plus 1. The tan squared theta plus 1 is just secant squared. Take the square root of that, you get 2 secant theta. I'm skipping a few more steps now than I did at first on these types of problems, but now that we've kind of seen how this works, maybe that's okay. And now that I've identified all the parts of this, now we can say the new integral. We've got an x up there, an x up here by itself. Well, we've already solved for x, so we know what x is going to become. We get -2 plus 2 tan theta. That's the x that we see in the numerator. We've got the dx also there, right? 2 secant squared theta. In the denominator, what do we have? We said all of that is going to become 2 secant theta. So we can cancel some stuff out, right? Those 2's are going to cancel. Secant will cancel with that secant squared up there. We're just left with 1 secant. So the new integral that we have here is going to be, let's distribute that secant that remains. We're going to have -2 secant theta. And we're going to have a +2 secant theta tangent theta. Next, those two integrals are actually, we don't even have to do any work on them. We've already seen how to do the integral of the secant function. So ln secant plus tangent. By the way, for future reference on the test, if you see the integral of the secant function, I would not require the work for that because we've done it already. That would like qualify as one of the ones that's just sort of a basic trig integral. And I would even say the same for the secant cubed at this point, since we've done that a couple times. If you remember what that is without doing the work, it's welcome to not do it, not do the work. And the antiderivative of secant tangent, that's another one that's just hopefully pretty easy for us. The antiderivative of secant tangent is just secant. So this one didn't require any substitutions or anything like that. All right, now we got to come back and change these back into x's, right? And so we have our original substitution up here. We said that x plus 2 is equal to 2 tan theta, right? I'm looking up here. That was our original substitution, right? With that in mind, we can solve that for tan theta, right? We can say that tan theta is equal to x plus 2 over 2. Okay? Tan theta is x plus 2 over 2. Well, if that's the case, then I can draw theta. Here's theta inside the triangle. I know how the tangent is defined. Opposite over adjacent. X plus 2 over 2. The third side then has to be the square of the first one. X plus 2 squared. Plus the other side squared is 4, right? So 4. So x plus 2 squared plus 4. Now that's the version of that we got after we completed the square. But if you remember, if you sort of went backwards on completing the square, x plus 2 squared over 4, right, this is in fact equal to that. And again, that is what showed up in the original integral. So what I said before about, that always happens, that happens here too. So you could in fact even write that that x plus 2 squared plus 4 in the original way if you wanted to. Right? So you could write it as, what was it? X squared plus 4x plus 8. You could write this as x squared plus 4x plus 8 if you wanted to. Okay, so now the last step is just to plug everything in, right? So this is equal to -2 ln secant theta. So secant again is defined to be hypotenuse over adjacent. So we're going to get square root squared plus 4x plus 8 over adjacent 2 plus tangent. Tangent's opposite over adjacent. Oops, there's no root there. So x plus 2 over 2. And then plus 2 secant theta. Again, secant, same thing. Square root x squared plus 4x plus 8 over 2. And then finally, simplify this. 2's here can cancel. And we can write this as minus 2 ln absolute value square root x squared plus 4x plus 8 plus x plus 2, all this divided by 2, plus the square root of x squared plus 4x plus 8. So there we go. Now, I do want to point something out about the book and the way the book would put this answer. So if you, I don't know if anybody's doing this, but in the ebook they have the end of the, in the homework problems section in the ebook, all of the odd numbered problems, you can just sort of hover over them and it'll tell you what the answer, I think you have to click it actually, but it'll tell you what the answer is. So like if you were trying to practice some problems or something and you wanted to see if you got the right answer, go to the ebook and check. What you would find in a problem like this, I just want to warn you about something like this, is that they would actually not put this 2 down here in the denominator as the answer. Now, why not? Why wouldn't they put that 2 there in the denominator? So they would actually just, it wouldn't be there in the answer at all. Let me point out why that happens. Because remember that you have this nice property of logarithms, right? When you have the logarithm of something divided by something else, right? Isn't that the same as, can you use the properties of logarithms to change that into subtraction? Remember that ln of a over b is the same as ln of a minus ln b. So in fact, I could write this then as this. Because the minus, but then there's also a minus here, right? And so those 2 minuses would become a plus. And then, I could get this. Right, so this is just using properties of logarithms. Now, why can we just neglect that 2 ln 2 entirely? Because, look, it's a constant, right? This is a constant. Well, we have this plus c on the end here, which is also a constant. It's just any constant. Anytime you have a constant, unknown constant, plus some other constant, you can just sort of absorb this constant into that one. Okay? And so basically this thing here, the 2 ln 2, just gets absorbed into the plus c. And you don't even need to write it anymore. It's just part of the constant. So as the final answer, you end up with this. So I'm just trying to point out that if you end up seeing this like in the book or whatever, or even on WebAssign, where they just toss out that extra piece, maybe you see that the answer doesn't have that 2 in the denominator, you're expecting to see it there. This is why that happens. It's because of properties of logarithms producing a constant, which would then be absorbed into the other constant.